Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Hey, step on inside. We are starting a brand new unit on radicals. We did rationals, and now we're doing radicals. Rationals are the ones with the fraction things. Radicals are the ones with the square root thingy. And that's, or cube root, and we're going to be dealing with both of those. Graphing today. Graphing square roots and cube roots. Not getting too deep in the whole big idea on how we simplify and solve these in big bad ways. We actually need to know less about that. Here we just need to know how to take a square root of something and cube root of something, like a perfect square and perfect cube, which we know how to do, and we know our transformations on A, H, and K. If you haven't been to my channel before, and if you haven't seen most recent videos on transforming involving the letters A, H, and K and parameters, you'll have to probably watch some of those or just really get up to speed with what I'm doing here, because I'm going to be talking about this in a way that you've probably understood some of this. Little solution guide video, 6 graphing square root practice problems, 6 graphing cube root practice problems using just A, H, and K. I do want another video in the future here, really soon, to be dealing with some negative x values as well, if we can. Until then, let's go ahead and jump straight into the action. Here we have a black screen. Here we go, white screen. And let's do the following. We're going to be sketching the graph of each function. Now, for the square root ones, I will also include talking about the domain and range, getting the understanding of, we have a limited domain and range when it comes to square roots. The idea of square roots, guys, is we cannot take square roots of negative numbers. And really just to talk about the whole thing of what's happening here is, graphing like a squared function, some sort of x squared thing, would leave us with a parabola, right side up, upside down, whatever it is. Well, these ones are going to be sideways facing parabolas like this, only it's not a full parabola, it's just going to be half a parabola. You're going to have that vertex idea, and it's only going to go in one direction, upward or downward. You can't have both because you can only have one y for every x value. I plug in some x value, there's only one y value that I'm going to get. That's how functions work. As opposed to the fact that you can plug in 2 different x values and get the same y value here. That's totally allowed. You just can't get 2 different y values for the same x value. So square root functions are going to have not only a limited domain because we can't take square roots of negatives, but they will also be half parabolas. And all we have to do is just make sure that we know how to take square roots of values, and we should be good. So as far as graphing these ones here, we have to know this form that looks like this. Y equals a times the square root of x minus h and then plus k. Now this should look very familiar to those who have been with me here in the past or recently as far as what a, h, and k do. They don't change as far as their role, as far as what they are actually meant to do. A represents your vertical stretch factor. Now we're used to parabolas being stretched skinnier because that's a vertical stretch. Well, these graphs that are going to kind of look like this are now going to be vertically stretched this way. They won't get skinnier. They will get, I don't know if you can say wider. There's no bottom end of it, but they're going to get taller. They're going to get taller as you go further out on x. Now your h and k represent your vertex value. Your vertex is at hk, in that you flip the h value sign and you keep the k value sign. You've probably seen it before. And that's as basic as we're going to get here. Obviously a might be a fraction. We'll see where we go from there, but I'm going to plot as many points as I can fit and move from there completely without a table. All right, so for problem number 1 here, we have y equals the square root of x plus 4 and then minus 4. So as far as pulling out information, there would be a 1 in front of here, if you can imagine that. So the a value is 1, and that vertex is going to be at negative 4, negative 4. And I mentioned negative 4 for x as we flip the h sign. So negative 4 down right there. Now every point that we're going to get off of this is just like how we would for quadratics and cubics and rational functions and such. It's all based on the behavior of the function. This function is a square root. And what are we going to do with square root functions? We're going to take the square root of however far we displace ourselves in the x direction from here. If I go over 1, I'm going to be going up the square root of 1. The square root of 1 is 1, boom, like that. Now, we might multiply by vertical stretch factor in the future, but as this one's just a 1, it's going to be basic. I'm going to keep it like that. When I go over 2, I'd be going up the square root of 2. Now, we don't really know what that is. I know it's around 1.4-ish, but I don't really know that number. So I'm going to be fine not taking square roots of values that I can't really do. Same with square root of 3, right? It's around 1.7, whatever, but it's not perfect. Square root of 4 is 2, and I can go 2 up like that. So again, 1, 1, 4, 2. Hey, this sounds a little bit like 1, 1, 2, 4, only it's inverted, and that's exactly what this is. It is the inversion of that. Square root of 5, 6, 7, 8, 9. You can take the square root of 9. That's 3. So I'll be going 3 up like that. So again, the idea is take the square roots of values that you know how to do. That's going to be pretty straightforward. If you want to try and get the decimal ones, more power to you. But plot the ones that you can and kind of go off of that. And there is going to be my curve. Now again, we're not going downward in this thing. It's possible they go downward, but they only go one direction. It's not a full parabola, it's just a half parabola. You can only get these y values by plugging in those x values. I plug in -3, I'm going to get -3. I plug in 0, I'm going to get -2. You can try it for yourself. Now, I want to speak on the domain and range stuff. So when it comes to this here, domain asks you, and you can answer these after you draw the graph if you'd like to. Domain asks you what values of x exist in this graph. You know, we've talked about, we didn't really say the word domain, but we've talked about restrictions with rational functions, and we were referring to domain. We were saying what values of x are allowed to be used or not allowed to be used. In terms of rational functions, we got to make sure that we don't plug in an x value where we divide by 0. When we have a radical function such as this, we want to make sure we plug in an x value where we don't get a negative inside our square root. So this quantity right here, this x plus 4, cannot be a negative number. This x plus 4 has to be greater than or equal to 0. So as an inequality, if I subtract 4 from both sides, what I'm really stating here is that this x has to be greater than or equal to -4. You can see where that -4 kicks in with the vertex right there. That whole flip the sign thing, we got to see what value of x would be plugged into here such that we get 0, because that represents the minimized x value, or the furthest left, in our case, furthest left x value that we can have there. And that's where that -4 really comes from in the vertex there. That is the smallest x value we can use. You plug in -5, you know, you get a negative number inside of here. You plug in anything greater than -4, you know, like -2 and 7 and things like that, you're good. You have a square root of a positive. All right, now the range is something you really do want to look at the graph with. It's harder to play with when it comes to plugging things in. You can do it, but you also want to know which direction it goes. So the range is going to be y is greater than or equal to, what's the lowest y value? Also -4 there. Honestly, it's the two vertex values. That's not going to be very difficult to conjure, but this really helps you make sense of it, and this will help me in my future video or videos when I talk about negative x's, things inside of there that can make the graph go to the left instead of to the right. So again, this graph can't go to the left. You know, this is your restricted domain. You'd get square roots of negatives. Those are non-real values. And there we go. Anyway, I want to do a little less on domain and range when I talk about it, but I did want to bring home the idea of the -4 there and how it comes into play, etc. So the rest should go significantly faster unless I got to talk about something new. Number 2, y equals 2 times the square root of x plus 1. And if you want your plus k, that would be a plus 0 in essence. So you have a stretch factor of 2, a vertical stretch factor, and a vertex of -1, flip, keep 0. So we're going to start at -1, 0. We're going to vertically stretch all our values to 2 and go from there. So we start from here. Now the points I'm going to put next are going to be temporary. Ordinarily, as you saw last time, we would go 1, 1, 4, 2, 9, 3. Yeah, we would take those things there and we would say, all right, we're going to do that. But we have to double those heights and not double the distance this way. It's not 1, 2, 2, 8, 1, 2, 8, 2, I should say, and 18, 3. We have to double the heights. So instead of 1, 1, it's going to be 1, 2. Instead of, they all move together. Instead of 4, 2, it's going to be 4, 4, double that height. And instead of 9, 3, it's going to be 9, 6. So everything is doubled in height from there. Again, saving your need for using a table here. You really want to save that need, especially here, because, you know, here you're not going to luck out as much as far as what to take square roots of. You're going to plug in numbers randomly and ask yourself, is this a good value to use? And when you take the square root of something that's not a perfect square, you're going to regret it. So I really recommend you just displace yourself. You plot the vertex, you displace yourself from the vertex, and you know what your perfect square values are. 1, 4, 9, 16, etc. Your domain here, if x plus 1 has to be greater than or equal to 0, x has to be greater than or equal to -1. Again, that's the vertex value here. Your range is looking at the graph, all y values are greater than or equal to 0 as we stay above the x-axis or on it. All right, number 3, we have our dosage of a negative right here. Y equals -4 times the square root of x plus 3. Now that square root of, the 3 is outside of the square root function in and of itself. So this is the k. If you wanted to get this in like a hk kind of way, this would be x minus 0. Right, so as far as vertex goes, that's at 0, 3. That a value is -4. But I'm going to start at the vertex. I'm going to start at 0, 3 right here. So that might help you a little bit as far as, writing it like that. All right, the negative is what flips this thing over. So instead of going this way, we are going to be going this way. So just whenever I say 1, 1, things like that, or whatever I say, make sure that I'm going to go down as I go right. The y values flip over. So the -4 means we're going to quadruple our heights. They'll be 4 times taller. So we'll see how low we can actually even get before we run out of room. So instead of 1, 1, assuming we're going downward, instead of 1, 1, it's going to be 1, 4. Whew, that's low. And instead of 4, 2, right, square root of 4 is 2, we got to quadruple the 2. That'll be 8. 2, 4, 6, 8, like that. I don't know. I don't think I can really fit this next one here, but 9, square root of 9 is 3, right? Maybe we can fit this. We'll get close. Where are we going? Square root of 9 is... Wait, that's not 9. Wait, 9's way over here. Hold on a second. Have I been graphing these correctly so far? You know what? I messed up. I'm sorry. I messed up this graph right here. I'm used to something. I beg your pardon on this graph. Give me one moment, guys. That should be right here. There we go. All right, my bad. Okay. I forgot these go up to 8. I was thinking they go up to 10, or I don't know what I was adding. I'm not sure. 9. Yeah, 9 goes off the graph in this way as well. Did I do this other one correctly? I guess I did. All right, so 9. Yeah, this one would be off the graph, right? What happens when you 3? 9, 3 times 4 is 9, 12. So that's 11. So it's somewhere like over here. It's not perfect, but I'm just getting the point so you can just, get the idea of it. I like to make a better looking version of that curve if I can. It's cool. It's kind of a nice smooth progression downward this way. I like that. I like that curve. All right. So there's that one. The domain here, x has to be greater than or equal to 0, right? Straight up. The idea inside here is 0 or more. Now the range here, this time it's y is less than or equal to. Y is to be less than or equal to 3. Or y is, not to, has to be, but that's what they become. Those are the y values you get out from there as it goes downward this time. All right, that is number 3. Let's go to number 4, another quadruple action here, and we are going to look at a vertex of, looks like 1, -5, with the a value being 4. All right, so we're going to go 1 over -5 down like that. All right, so quadrupling, we are going, instead of square root of 1 is 1, square root of 1 times 4, 1, 2, 3, 4, like this. And then square root of 4, 1, 2, 3, 4 is 2. Let's quadruple that, 2, 4, 6, 8. And really, I do think that's all I can fit this time, so I'm not going to bother with the 9, 12, or 9, 3 quadrupled, as you want to put. Okay. Very quick one. So you can see where I'm going from that. Domain, x is greater than or equal to 1. And again, if you saw what I did last time, we're saying what's inside has to be greater than or equal to 0. So x minus 1 has to be greater than or equal to 0. You add 1 to both sides, x has to be greater than or equal to 1. And like I said, a range is better served for the graphs. I know we already did the graph here. In fact, on 5 and 6, if you don't mind, I'll do the domain first. I'll compute the domain first, and then we'll get the range after we graph. But the range is y is greater than or equal to -5. Again, they have to do with the vertex values. Okay, number 5. Numbers 5 and 6, last two square root ones. You can see how this really starts to speed up over time. So this time, like I said, I promised I would do the domain first here. So on number 5 here, we are going to be doing, just kind of stating how x plus 3 has to be greater than or equal to 0. Subtract 3 from both sides, x is greater than or equal to -3. So, when you see the graph, that's something you're going to recognize, that we have to go to the right from -3. And that makes sense. Your vertex is at -3, 2, with an a value of 1/2. There's that fraction I may or may not have promised. So we are at -3, 2 right there, and this graph will go to the right. Our x values need to be greater than this number. Now, I'm still going to be taking the square root of 1 and 4 and 9. But now we have to compress, vertically compress our heights. We're going to halve them, divide them by 2. So instead of 1, 1, it's going to be 1, 1/2. Instead of 4, 2, it's going to be 4, 1. And instead of 9, 3, it's going to be 9, 1.5 right there, or 3 halves if you want to say that. So a little one of those skinnier ones. They're not my favorite flare-wise because they don't give as much character to the thing. It makes it look like I'm going horizontally when I'm truly not. But I'm trying. All right. The range of this thing, now that you see that graph, you can see this graph goes upward here. That is y is greater than or equal to 2. Yes, you can do domain and range without doing the graph. If you understand that it starts from the vertex, if you understand that it goes upward, things like that, you will be fine and fare well with it. But you can also look at the graph and do it to confirm that everything works out. You'll really see that domain will play its hand a lot more when we deal with negative x's, meaning a negative inside of here, which is possible to have. No square roots of negatives, but you can have a negative x. Because it makes the graph go left, and we can talk about why that does it when we refer to domain stuff. All right, lastly, number 6, before we do cube roots. We have a -1 on the outside. That's an a of -1. Flipping our graph over, our vertex is going to be at -4, 3. Can you imagine what domain and range is going to be without graphing? As all these graphs will be going to the right, because no negative x's here, our domain is going to be x is greater than or equal to -4, and y is going to compare to that 3, right? Will it be greater than or equal to, or less than or equal to? Well, this graph is going to top out at its vertex because it's only going to go down from there. So every y value is going to start at 3 and go lower from there. We start at -4, 3 like this, and with that -1 stretch factor, we're going to be going square root of 1 is 1, down. Square root of 4 is 2, down. Square root of 9 is 3, down. And there will be that graph there. So again, domain and range, not too much of a hassle there. But it's a portion of square root graphs that we should probably pay attention to. Especially, like I said, when we start dealing with negatives inside the square root, negative x's. All right, so those are the square root graphs. We'll now go to the cube root graphs. And in these ones, guys, I will not talk about domain and range. And the reason for that is simple. Cube root graphs have all real number domains and ranges. Unlike square roots, where you can't take the negative of a square root, you can take the negative of a cube root. Because when you cube a negative value, your result is negative. See, we can't take the square root of a negative because when you square a negative value, you get a positive like that. But if I cube a negative value, I get a negative, right? So the whole idea of square root of -9, it's not real. It's not real. But the cube root of -27 is totally a thing. That's -3. So when we're doing these things here, understand that we can go in the negative and positive direction. We don't have something called a vertex, but we do have a reference point called the center, or at least what I'm going to call the center of this thing, because there's symmetry around that point. Okay, but everything behaves the same as we did before. So this is going to be a form of y equals a times the cube root of x minus h plus k. And a, again, is your vertical stretch factor. H and k represent that reference point, this time known as the center, hk. Nothing really changes there, only now the behavior of this thing is going to change because it's cube roots instead of square roots. So know your perfect cubes. The cube root of 1 is 1. The cube root of 8 is 2. 8 is a perfect cube. And then -1 and -8 we can take cube roots of as well. So number 7, we have a 1 in front of here. If you remember, this cube root of x would be x minus 0. Your h value is 0. Our center here is going to be at 0, -5. That's the k for the center. So 0, -5 is going to start right down there. And we have a 1 stretch factor, which tells us that as we go over to 1, we're going to go up the cube root of 1. As we go over 8, we'll go up the cube root of 8. So 1, 1, 8, 2. Now when we go -1, the cube root of that is -1, and the cube root of -8 is -2, like this. So we'll have a graph that sits pretty, going like that, very sharply approaching this center fold right here, and curving itself back out. Like that. All right. Now this has an all real number domain and range. I'm not even going to list what they are. This goes forever left, forever right, and believe it or not, forever up and forever down. Sure, it's not very sharp as it goes forever up and down, but it sure does. It doesn't flatten out. Just like cubic functions never go fully vertical like this. Cube roots don't go fully horizontal. All right, number 8 here. We once again have a 1, a value of 1. It looks like a couple of these will be 1. Let's change colors. The a value is 1. And then your center is going to be at -4, 0, understanding that's a +0 right there. So I'm going to start right here as far as center goes. And the a value being 1 does not change how we did the last set here. Cube root of 1 is 1, so 1, 1, 8, 2. You know, the other one's just way too far out. We're not going to find it. 3 cubed is 27. So you'd have to go 27 away on x to find going up 3. You can see that's really how flat it goes. And on this side, I can honestly only fit the -1 portion. I can't even get to that 8, the -8, -2 idea. So again, can't really do too much on that there. Just do what you can as far as plotting that graph. Best of luck to ye. It's good enough, honestly. There's our symmetry. All right, number 9. You know, not much is changing here until we hit the last 3 with different stretch factors. So we have, once again, an a value of 1 as the stretch factor goes, and our center is at 3, 2. So I'm going to start right here at 3, 2. Stretch factor of 1 doesn't change. 1, 1, 8, 2, 6, 7, 8, right? It's somewhere over here. I'll just give a little reference point. That's good. All right, -1, -1, and -8, -2. So again, just going without a table, guys. These can be very, very fast graphs, and you can make sense of them and be efficient with them if you know what you're doing. Nothing's gonna stop you now from being a good kind of grapher when it comes to cube. I'm saying that, but I can't do this. The problem is I'm not doing it on the screen. I'm doing it on a tablet that's hard to maneuver with. It's not like paper. Your arm gets locked up on it. I'm trying my best to do those parts. I do apologize. Honestly, this shouldn't slant through like this, guys. It should really plateau itself off like this. Okay, that's what I'm trying to do with these graphs, and it's not really. That's a little better. All right, these next ones will have different stretch factors here. A 2, a -3, and a -2. So, number 10. Let's do this color. Okay, H and K. All right, looks like we're starting at the origin this time, right? There's -0, +0 kind of thing. Our center is at 0, 0 with a vertical stretch factor of 2. So now we get to play with some stretches. Let's go ahead and do that. We are starting at the origin here. Perfect. Cube root of 1 is 1. Let's double that. Cube root of 8 is 2. Let's double that. See that? -1, cube root of that is -1 doubled. Cube root of 8, -8 is -2 doubled. And those are our unique points to get into as we go through the graph. Oh boy. See, I want to make it good for you. Oh, that's good. Oh, that's good. I want to make it brand new and exciting. That's a good one. Okay, 2 more here. Let's try and beat the 25-minute mark. I don't know if we can. All right, number 11. Center is at -5, what? 0, right? The +0 there. Your stretch factor is -3. So, you know, pay close attention to that one. So we're starting at -5, 0 here. Stretch factor of -3 means it'll flip over. So we're going to go down as we go right. And then we got to triple our values. It's not 1, 1, but it's 1, 3. And it's not 8, 2, but it's 8, 6. Because we got to triple that 2. And this side, I can only really fit the 1, 3. I don't really know what that'll look like on that side, right? It's really hard without that second set of points. I really got to curve it off in a nice symmetrical way that I just did coming from over here. So let's see. Looks like that's going to take it and kind of going like that. Not bad. Honestly, you don't need that much, but you do need to send it off, right? You need to send it off in that direction. It really should be a smoother curve than where I made it. All right, last one here, right? This is all we're doing for these things. Domain and range, all real numbers. Guess I can't beat 25 minutes. I could if I didn't write the information. All right, let's do black. The center for this one is at -2, 2, right here. Stretch factor is -2. So again, it'll be going down and we'll be doubling those heights. I really should have done a fraction one, huh? All right, so 1, 1 doubled. 8, 2 doubled. 1, 1 doubled. And 8, can't really fit it, but I will. 8, 2 doubled. When I say 2 doubled, that's 4. And 1 doubled is 2. All right, last graph. Sorry. Sloppy, sloppy, sloppy. Not good. Hold on. Should go more like this one that I'm about to do next. Oh, except for that very ending. Okay. All right, anyway. So that ought to do it for this one, guys. All right. This is Mr. Robinson. Thank you so much for watching. I hope that made sense as far as what we're doing in a tableless manner, given the transformations. Next time you see me do any things on graphs, I sure hope I can do ones with negatives in front of the x's so we can also flip them over horizontally and talk about how the domains are less thans for x as we can do that. All right, guys, that's it for this one. Thank you so much, Mr. Robinson. See more with me on radicals soon. Take care.